Good morning, everyone. Welcome back to class. Hopefully midterm one went well for everybody. We will have scores in as soon as we can get them in. There's sometimes a lengthy process where they don't quite get in as quick as you would hope they would get in. Probably Friday into Monday. It's probably when scores will go up. The actual seeing of the questions is usually a few days after that, so you may not see the actual questions to review your actual answers and the key and all that until a few days after you see your score. But just to give you an idea of what that looks like, it's going to be a couple of days before we see that. Overall, I can kind of see the average already. It's like in the 80% range. And that's kind of where, if you recall, the first day I was predicting. Midterm 1 is usually the easiest of our exams. It doesn't mean midterm 2 can't have the same average. It's just typically it doesn't have the same average. Now, one of the reasons why is that sometimes we get a little complacent. Not necessarily you guys here today, because you guys came the day after, the lecture after midterm. It's common to skip this lecture and to kind of like take the rest of the week off. Obviously, you guys aren't doing that, so that's like the first step is kind of, as you start to approach the next set of material for the next midterm, is to take in each lecture, try to keep up with each lecture, try to do some reading if you need to, do the homework set. Hopefully those problems make sense. If you take a quiz or two between now and like the weekend, that'll hopefully solidify what we're learning and talking about. And probably the big thing is like whenever something is confusing, if you try to make that unconfusing, if you go through the process of coming to office hours, seeking something out in the book, looking at a lecture video, rewatching that part of lecture. If you just take the effort to take something confusing and make it something you understand, then you're that much better off heading into the next midterm. If we're the weekend before, the next midterm trying to piece all of that information together, then that's when things get a little chaotic. If you look at a practice midterm and you're kind of going through each question going, ooh, these look kind of scary, I don't really know most of these problems, then that's kind of like a 2 week ago problem that we solved by 2 weeks before that point, putting in a lot of work and effort and kind of, in that word, like trusting that process of like, if we go through the study cycle process of come to class, review our notes, do some homework, practice quiz ourselves, and rinse, lather, repeat that process, I think we'll be more than prepared heading into midterm 2. The material will pick up and be a little bit more challenging here in midterm 2 as well. So some of the topics in chapter 1 are pretty, relatively straightforward. I think they're straightforward in the whole class, but of course I've been teaching this for like 20 years. So of course it seems easy from my vantage point, but I think from a lot of your guys' vantage points, probably most of this class is review from stuff you've seen from high school with maybe just a little bit more emphasis on some of the details and how some of these topics are linked together. So probably for a lot of you guys, this is material you've seen before. Whenever you get to a chapter or set of material that's new, that you're looking at something and saying, I don't remember this at all from high school, that's where I kind of start to think detailed read a chapter, spend more time like in the reading part of the chapter. And if we're mostly in the review mode, then I think that's a little bit easier. Then that's more like skim mode in the book. That's just looking at homework problems, piecing together a lecture and kind of going from there. Okay, so with that, we're in the middle, or not really in the middle, we're kind of like in the midst of the early part of chapter 3, looking at chemical reactions. But we also, in this chapter, introduced the concept of the mole. And I want to take a little bit of time just to kind of remind ourselves that we're balancing reactions. That's just making sure the left and the right side are balanced. That's pretty straightforward, having the atoms in balance in the reactant and product side. We introduced combination, decomposition, and combustion reactions. Combination is just combining two or more reactants into a single product. Decomposition is the opposite. It's taking a single reactant and decomposing it into two or more products. And then the combustion were the hydrocarbons plus O2, oxygen gas forming CO2 and water. But let's look at Avogadro's number and kind of go back through where this number kind of comes from and its relevance, what it means, and start to get into some examples of it. I think this is probably one of the more misunderstood concepts in chemistry. That is, when you look at it again, maybe a few times, it starts to make sense. That the whole idea of where Avogadro's number comes from starts with this. You start with the carbon-12 atom, and then you just say, for this one single atom, you take one carbon-12 atom, and you just define that mass. I know my handwriting is terrible. Let me try to rewrite atom. So you take a single atom of carbon-12, and you just say and define that this has a 12 AMU mass exactly, just by definition. So you just look at a single carbon atom and say for one single sphere of that atom that of course is really, really small, One of there's a length scale in chapter 2 that I didn't really get to talk about, which was the angstrom scale. A problem or two in the daily quizzes had that angstrom unit. The diameter of a carbon atom is about 1.5 angstrom. So the diameter across the carbon atom is about 1.5 angstrom. An angstrom is just a 10 to the minus 10 meter. And so this is just equal to 1.5 times 10 to the minus 10 meter. 1 angstrom is a 10 to the minus 10 meter. We'll use that unit more later. You probably won't need it for anything in chapters 3 or 4, but I just hadn't talked about that unit yet. I just wanted to make sure I threw that out there, that this single atom is about 1.5 angstrom in diameter for a carbon atom, and that's really small. That's a 10 to the minus 10 meter. Okay, so we take this one single atom and we just say, let's just define and say and agree that its mass is 12 AMU. We just completely make up this scale, the AMU scale. But then you say, well, let's take an actual mass of carbon-12 that we can measure. So if you take 12 grams of carbon, as precisely as that can be measured, and you're specifically taking carbon-12, an enriched sample, where you have 100% or as best as you can have that sample, just the carbon-12 atom, you then say how many atoms of carbon-12 are in that precise or that as exact as you can measure out 12-gram sample. And then you start counting. Luckily, we don't count individually because this would take a while, but the count comes out to be 6.022 ... It's 14076. Not that you have to have those memorized, but if you teach a class for 20 years, you start to memorize a bunch of digits like that. But it's times 10 to the 23 carbon-12 atoms. So you take the actual mass of a sample that you can measure, and you can count the atoms, and that's the count that you come up with. And then the only reason maybe why I might emphasize that number is that then becomes like an experimental measurable value that we have some fundamental limits on how precisely we can determine it. And obviously this is an important number, and so we're pretty precise here, but we can't be like, we can't be exactly precise. So we get to however many digits that is, 1, 2, 3, 4, 5, 6, 7, 8, 9 digits, 9 significant digits on this number. If you look at the speed of light, it's also a similar number that we measure, and it has 9 or 10 digits that are known. And we hit a limit just of how well we can precisely define the quantity. And so that's where the idea of the mole comes from, is we just then say, well, let's take this count of atoms and just define that to be what a mole is. So we say from this number of atoms that we can measure experimentally, that this is what we're defining to be 1 mole. And then when we say a mole, then that can just be a conversion factor, that 1 mole is just that number of the thing that you have a mole of. And then that becomes kind of a tricky part of, well, what do you mean by mole? Well, this little question here, how many total atoms are present if you have a mole? Imagine a container could be a balloon. If we had a balloon filled with helium gas, if you've seen the ideal gas law stuff, we'll see this in chapter 10, you might know a mole of a gas at STP, if we go to 0 degrees C for this balloon, so we're in a cold room, it would have a volume of about 22.415 liters. So just get a sense, it'd be a big balloon. So if we had a balloon of helium, there'd be an Avogadro's number of helium atoms in this balloon. So the way we'd be looking at Avogadro's number for this conversion here would be 1 mole of helium. For every mole of that helium, we have an Avogadro's number of what this is. That's a helium atom, so I have an Avogadro's number of helium atoms. So I'd have 6.0 times 10 to the 23 helium atoms in that 1 mole sample. Now, what if I had a mole of H2? I think you can see it here, that you'd have a mole of H2. So you'd have a mole of the molecule of hydrogen. So if you have a mole of H2, you'd have, for every 1 mole of H2, you'd have 6.022 ... times 10 to the 23. We'll just go to 4 sig figs here, but it's H2 molecules. So you have to look at a mole of like X is an Avogadro's number of whatever X is. For helium, helium's an atom. So a mole of helium is a mole of helium atoms. A mole of H2 is a mole of H2 molecules, where each molecule, 1 molecule of H2 contains 2 atoms. And so if we want the atom count, then we just simply need to use a conversion here that 1 mole of H2, or excuse me, 1 molecule of H2 contains 2 H atoms. So we have 2 H atoms per mole of hydrogen. So we're going to have 2 times Avogadro's number of atoms. Debating on, I'll just erase this here to be able to write in. So that would work out to be 2 times 6.0 times 10 to the 23 H atoms. So that would be 1.2 times 10 to the 24 H atoms. So a mole of helium is just Avogadro's number of helium atoms, but of H2, now it's like we have double the number of atoms. Yeah.
What is on the bottom of the conversion factor to H atoms? Like what's under that?
Molecule of H2. So,
Okay.
yeah. And let me go through this. I'll write it down below so I have a little bit more room to write, and hopefully it can be more clear for the CH4. So we're just trying to say you're going from a mole of H2 to an Avogadro's number of molecules of H2, and then you're going a molecule of H2 to the atom count within H2. And so let me write the CH4 down here. So the number of atoms total present in 1 mole of CH4, how I would approach this is that for every mole of CH4, there are precisely 6.022 times 10 to the 23 CH4 is a molecule, so CH4 molecules. Now, if we want an abbreviation for molecule, we don't want to use mole because that would be confusing because that's a big quantity. A mole is an Avogadro's number of something. A molecule is just one specific entity. It's just specifically 1 C atom, 4 hydrogen atoms. And so if I want to use an abbreviation for molecule, probably the best one's mol C. So if I want to say for every 1 molecule of CH4, I probably want to use that abbreviation just to make sure we're clear in our writing and when we're writing things out that we mean for one of those specific molecules of CH4, how many total atoms are there? There's 5 atoms. There's the carbon, of course, and the 4 hydrogens. So now that's probably going to be 3.0 times 10 to the 24, but let's just do the math. Yeah, 3.0 times 10 to the 24. Okay, so in 1.0 mole, so a container has a mole to 2 sig figs of CH4. We end up with 3.0 to 2 sig figs times 10 to the 24 molecules of CH4 in that container. And so hopefully just like seeing that you can have a mole of anything. You can have a mole, it's just like saying you could have a mole of a dozen of eggs. That would be 12 times Avogadro's number of eggs. That would be an ungodly number of eggs, of course. There's an example where if you were to have an Avogadro's number of nickels, so if you took an Avogadro's count of nickels and tried to circle the equator of the Earth with those nickels, you can make it around the Earth 300 trillion times. That's just how small the atom is. So the atom has that in a 12-gram sample of carbon, a couple granules of carbon. Like 12 grams is, it's a teaspoon of sugar is about 12 grams to give you a sense of just how much mass that would look like. If you had that much carbon, if that were pure carbon, that would have that would have 6.0 times 10 to the 23 carbon atoms, and that those atoms must be quite small. So if you made the atom much bigger, if you made it the size of a nickel and circle the Earth 300 trillion times. If you actually just take the atom itself of its actual size, if you take a mole of carbon and try to go to the sun with it, you can get to the sun and back like a couple 100 million times, just with the actual size of the atom. That's how small the atom are and how many atoms there are within an ordinary size sample. So just a few thoughts on just how small the atom is in terms of how small that mass is and how plentiful the atom count is within molecules. Now let's have one quick discussion here before we move forward on molecular weights, formula weights, molar masses. We were talking about this at the end of class. There's a little bit of lingo here on certain types of formulas aren't necessarily molecules. You know, so if I have something like C2H2, that's a molecular compound. So that's the molecular formula. And so this would have a molecular weight. This would have a formula weight that are both equal. We worked this out last time to be 26.04 AMU. That the molecular weight and formula weight are synonymous. There's no difference between those two numbers. And so you can think of a formula weight as the weight of whatever the formula is. And if the formula happens to represent a molecule or a molecular compound, then that's also what we would call a molecular weight. Now, if you looked at something like NaCl or whatever you would look at as being an ionic compound, that's just not a molecule in the same way that we think of C2H2. Now, the main difference here, it's kind of like useful to think of it this way, that if you had a sample of acetylene, that you're going to have a bunch of molecules that just have 4 total atoms that are separate from the other molecules that have 4 atoms. They'd be moving around in space separate from each other, not connected together. If you had a sample of NaCl, you'd have plus, minus, plus, minus, plus, minus if you had a solid sodium chloride. And you'd have just that one compound that's possible with that formula. And then you'd have an array of ions that are all linked together through electrostatic forces of attraction. So a much different type of compound. You really don't have like an NaCl unit, another NaCl unit in the solid, you know what I mean? You have them all arranged in an array. And so we tend not to look at NaCl as a molecule. So this isn't really a molecule. So we would just give this a formula weight. And so the formula weight would be like 23 for sodium, 35.45. So this is 58.45 AMU. And we would just call that a formula weight. Now in lingo, people they'll say, what's the molecular weight of NaCl? And you know, they're not really calling it a molecule. Like, so people will probably mistakenly use the word molecular weight a lot of times for an ionic compound. But I just wanted to differentiate that we would usually use the nomenclature that has sodium chloride has a formula weight. It's just the weight of that formula. Since it's not a molecule, we tend not to call it a molecular weight. Just a tiny nuanced detail there. But then we go molar mass, that the molar mass, the grams per mole, that the grams per mole is numerically the same number. So the molar mass of C2H2 is 26.04 but grams per mole. And the molar mass of NaCl, the mass per mole of NaCl, is just 58.45 grams per mole. So the molar mass is the grams per mole, and that's because the AMU to gram conversion, Avogadro's number and the denominator, and then the molecules in a mole conversion in the numerator is Avogadro's number. And so the way that we've devised this whole system using carbon-12 is kind of our starting point, counting the atoms, defining that count to be the mole, determining the AMU to gram conversion. I won't go through this derivation again, but on Monday, I was then saying, if you take the actual mass of that carbon-12 atom, you can calculate from 12 grams, Avogadro's number of atoms, you can calculate the actual mass of the carbon-12 atom, and then set that equal to 12 AMU and define and see the conversion factor for AMU to gram. And by the way we've chosen this whole system and structured it, it comes out to be exactly Avogadro's number. So you go AMU to gram, Avogadro's number denominator, you go moles to molecules, or moles to atoms, multiply by Avogadro's number, so the number cancels itself out. So that's why when you look at the molar mass of these values, it's 26.04 grams per mole, same number, 58.45 grams per mole. And a small lingo is that the molar mass isn't equivalent to the molecular weight, it's just the same number. It's the lingo would be they're numerically the same number or numerically equivalent. They're not equal because you're saying the molecular weight's the weight of one unit and then the molar mass is the weight of 1 mole. They just happen to have a very carefully, since we structured the system this way, the same actual number. So it makes it easy for us to calculate molar masses and molecular weights. Okay, so let's get into some problems that we can look at and just break down some other topics of chapter 3. One of those are percent weights and how we can calculate a percent weight. And we're going to see here in a few moments, and one of the more memorable problems to me from chemistry was going through the percent masses into a formula. So you're going to see we can take formula and get percent masses, And then, of course, you can take the percent masses and get a formula from that as well. So let's start the simple way and just say, well, what's the percent carbon and hydrogen in these two compounds, C2H2 and C6H6? So we're just saying, what's the percent carbon by mass? What's the percent hydrogen by mass? So the percent carbon, let's start with C2H2. The way we'd be looking at it is saying of the 26.04 AMU or the 26.04 grams per mole, how much of that mass is due just to the carbon? And so there's two carbon atoms. Carbon's atomic weight is 12.01 AMU. I'm going to use AMU here because I'm trying to think of just the mass of one molecule. We could do grams per mole. It would come out obviously to be the same number. But I'm just thinking two carbons have that mass. And then the mass of the formula for C2H2 is 26.04 AMU. So carbon represents most of that mass. So about 24 of that AMU is coming from carbon. So I want a percent, the mass percent here, just multiply by 100. So we're saying of the 26 AMU, 24 of that is due to carbon. If we're more precise, 2 times 12.01. We're of course just getting this from the average atomic weight of carbon on the periodic table. And so that's 92.24%. Now, if we're talking sig figs here, this is a weird topic. We could look up the atomic weights as precise as we can have them determined. So we could have been more precise here, but I'm just going to go to 4 sig figs. That's good enough for us to kind of see a comparison. Now, when I look at C6H6, what can you say about C2H2 versus C6H6? Obviously, they share an empirical formula of CH. Now, I mentioned before, because they share the same empirical formula, it doesn't really mean much. It doesn't mean that they share any properties in common with each other due to that fact. It's just more a consequence for this chapter that when we calculate or see a percent mass, of course it's going to have the same percent mass. Like the percent mass of carbon in CH is the same as the percent mass in C2H2 of carbon, and it's going to be the same as it is in C6H6. Let's make sure we see this and can work this out. So the percent carbon in C2H2 versus that in C6H6. So the percent C mass in C6H6 would be equal to now 6 times the carbon atoms. I have 6 carbon atoms here, 12.01 AMU each. And now we just have to divide by the formula weight of 6 carbons and 6 hydrogens. And so that's 12.01 times 6 plus 1.008 times 6. So that's 78.11 grams. Or I'm sorry, 78.11 AMU, because we're calculating just the molecular weight here in AMU. Multiply that also by 100%. And I think you know it's going to come out to the same number. $92.25. Now, the small difference in this last placeholder is just due to how I probably should have tacked on an extra sig fig or two to really see that agreement. Since I'm just using 4 sig figs on the masses, obviously the periodic table usually has a few more digits. So if we wanted to be super precise here, we could see that these are exactly the same percent masses. And so now what the consequence of this is one that when we give you percent by mass data, like if I told you a compound had 92.24 or 25% carbon by mass, you would know the difference was hydrogen. If I say you know the compound contains C and H, you know the percent hydrogen here has to be 100% minus this. So let's do that difference there. So that's 7.76%. Is the hydrogen percentage, because if it's not carbon, it has to be hydrogen in the mass. We could have done the hydrogen mass the same way. We could have done 2 times 1.008 or 6 times 1.008, divide by the formula weight of the 2 compounds and seen this number come out as well. But we know that the percent carbon and hydrogen have to add up to 100%. If it's not carbon, it's hydrogen, vice versa. And so what we can see is that if I give you now the percent mass, if I said in a different context, I said a compound has a carbon percentage of 92.24 and a hydrogen percentage of 7.76, what could you tell me from that data? The answer wouldn't be that it's C2H2 or C6H6 because they have the exact same percent by mass. The best you could tell me is the empirical formula. So when we give you percent by mass data, what you can determine from that, experimentally we can get percent by mass data. So if we get that data experimentally, then you can determine the empirical formula. And then if we then say, well, what if we do an analysis where we can get the percent by mass and we get the molecular weight? We can then determine a formula from that. So that's a problem that's coming either towards the end of the notes today or the start of class on Friday. So before we get to that particular problem, and probably again, I bring that problem up because that's kind of why we're talking about percent masses, because we're gonna see you can calculate masses from formula, you can get formula from the masses, but it's the empirical formula when you have the percent by masses. And that's also probably a problem you've seen before and hopefully can see us driving towards understanding that type of problem. So Avogadro's number, like how we're going from grams to moles. So if we get the mass of a substance, if I say you have 10 grams of water, how many moles? You would probably say, well, let's use a molar mass, grams per mole. So 10 grams of water, you then have 18.02, just taking 16 for oxygen, 2 times 1.008 for hydrogen. So 18.02 grams per mole for water. So you'd have like less than a mole of water and 10 grams of water. So we're gonna use a molar mass to convert between grams and moles. If we want to convert between moles, like say moles of water and how many molecules of water, the word particle here is sometimes used when the particle can be an atom, it could be a molecule, it could be a unit. And so particle is kind of what we're using for like helium. The particle would be an atom. If we had water, the particle would be a molecule, like water is a molecule. So kind of thinking, we say, what's the particle that exists in water? It's the molecule of water. So it's pretty obvious, but maybe not entirely obvious. And then another one would be like salt, NaCl. Here we would probably use either unit, is probably the best thing that we tend to say. So the particle within NaCl is just that unit, like one single unit of NaCl, where we tend not to call it a molecule. So when we say particle, this is kind of us trying to say, depending on what the thing is, it could be an atomic sample, it could be a molecular sample, it could be like a unit sample, like an ionic compound. And this conversion here goes with Avogadro's number. We symbol that N, capital A subscript. So that's Avogadro's number, allows that conversion. And then here we look at the formula. So we look at the formula to go from the units of the particle into the atom count. So let's go through a problem that kind of just goes through this range of conversions. I thought like a funny example, I always thought it on the first day of class would be interesting just to ask the question, how many molecules of water do you think are in like a 100-gram sample? And a 100-gram sample would be, that would be 100 milliliters. So you're not talking a lot of water. 100 milliliters is like less than a can of soda, worth of water. And so in that specific quantity, it's like how many jelly beans are in this dish? You see that thing like for like a raffle or something. Well, how many water molecules are in the container? And we got to count each one of them up. And of course, it's going to be a big number. And you may not just appreciate on the first day of class, or like if you go back like when you were like in 6th grade and get this question, you probably think, I don't know, maybe 10. How many molecules do you think would be in water? And it's like 10 to the 24 or 10 to the 25 number of molecules. It's such a big number. And so let's just try to look at this 100-gram sample of water and just go through calculating the moles, calculating the number of water molecules, the number of H atoms that would be present within the sample, and how many grams of hydrogen are present. Okay, so the number of moles. Start with the 100-gram sample. Now, when I use 18.02 grams per mole of water, I'm just looking at the 18.02 coming from 2 times 1.008 plus 16.00, 1 oxygen, so 1 times that number. And I can either go AMU for these, and that's the molecular weight in AMU, or just use grams per mole. So with this problem here, it might make more sense to use and treat the atomic weights as their molar mass quantities. So we're just determining and summing up the molar mass. So when I went through the painstaking process of saying, okay, it's 18.02 AMU, then we define the AMU scale and the conversion, the mole conversion, and we divide by Avogadro's number, multiply Avogadro's number. We don't need to do that every time. We can just use these numbers here as their molar mass quantities. And so the number of moles of water in the sample is just 100 divided by 18.02 is 5.549 moles of water. So just over 5.5 moles of water here within this 100-gram sample. Then the molecule count would be equal to that number of molecules, or that number of moles that we previously calculated. So for every 1 mole of water, so my mole of water to cancel out here, I have to think how do I use Avogadro's number? Well, it'll be 6.022 times 10 to the 23 particles of whatever that thing is, and that thing's a molecule. So I get an Avogadro's number of H2O molecules. So I just need to multiply the mole count by 6.022. Oh, I screwed up. So I get 3.342 times 10 to the 24 water molecules present within that sample. So big number, obviously. We were expecting a big number, and certainly this number here is pretty big. So that's the number of water molecules present within the sample. Now, how many total H atoms are there within the sample? Now, sometimes this problem is confusing because we're not saying that there's like free hydrogen atoms. When I ask this question, I'm just trying to say, if you just were able to say and quantify how many hydrogen atoms, it's kind of like if we just said like how many, I'm trying to think of a good example of this. Just like if you had, what's something that comes in pairs, like AirPods or something. So you have a case of AirPods. Let's say in a case of AirPods that there's 100 pairs of AirPods, but there's 200 AirPods in that case. So there's 200 total AirPods if you think of each pair having 2. It doesn't mean that they're then free AirPods. There's still each individually 2 in each case. So you can still say how many AirPods are there. Sometimes we ask this question, students get confused and they're thinking, wait, I thought hydrogen was attached to oxygen. There's no hydrogen in the sample that's free. We ask a question like this, we're just saying in total how many atoms of hydrogen are present within the sample in whatever environment they happen to be in. For every 2, they're connected to 1 oxygen. Okay, and so the number of H atoms would just be equal to, we'll take our molecule count, 3.342 times 10 to the 24 water molecules. And it's as simple as every 1 molecule of water contains 2 H atoms. So we just need to double that molecule count. And so that works out to be 6.684 times 10 to the 24 H atoms. So a lot of H atoms. We could have quantified the total number of atoms. The atom question is usually one that's just like, can we calculate how many of something there is within a sample? That just gets us into thinking of the formula and how that applies to the sample. And then how many grams of hydrogen does that represent? Like how much mass of the sample is hydrogen? Now there's a few different ways we could quantify the mass of hydrogen. I could take the molecule count. I could then use the mass per atom of H. I can then convert into the proper unit. I could go that route. Let's do that way first. So let's try to solve this last quantity 2 different ways. So method 1, we're just gonna take this atom count of, so the grams of hydrogen, I'm going to take that atom count that we just obtained. And then I either need to go to moles so I can use the gram per mole mass of hydrogen, or I need to use like the mass of hydrogen in AMU per atom and then convert AMU to grams. One or the other. So somehow I need to use Avogadro's number. It's just either my AMU to gram conversion or it's going to be in the molecule to mole conversion for hydrogen. So let's go to moles here because I think that makes a little bit more sense, or maybe it's a little bit more obvious why I'm doing this. Is I divide by Avogadro's number. I'm saying there's 6.022 times 10 to the 23 H atoms per every 1 mole of that atom. Okay, and then that lets me use from the periodic table the molar mass of hydrogen, where I can use for every 1 mole of hydrogen from the periodic table, that's 1.008 grams. So now sometimes, like we know, like this is a conversion we know. Like we know the molar mass of hydrogen, we can use that number from the periodic table. Like knowing that this grams per mole is kind of what told us would have been the cue on converting the atom count into moles in the first place. So like occasionally we get into these problems where the middle step of the dimensional analysis, you may not understand why we're doing it, but just know in order to use the grams per mole, we had to go atoms to mole to be able to use that conversion factor. Okay, so if we do that math there, I get 11.19 grams, which probably sounds about right. Of the 100-gram sample, 11.18 grams of that was due to hydrogen. So that's one way we can just take the atom count here, calculate the mass of hydrogen from that atom count. But if I also then said, well, if you know you have a 100-gram sample, and you maybe hadn't gone through steps 1 through 3 here first, and you just had the question, I just said, in 100 grams of water, how much hydrogen is there? You may have said a second attempt here would have been just to use that the number of grams of hydrogen could be calculated by taking the 100-gram sample mass that we had to start with of carbon and of hydrogen and oxygen, and multiplying this by the percent mass of hydrogen in water. So if we just said another way to approach this problem to calculate the percent by mass of hydrogen may have been just to say, well, what's the percent H in water? And the percent H in water is just 2 times 1.008 AMU divide by 18.02 AMU. That's our percent by mass. I'm going to leave that as a fraction. If you multiply a percent by a number, the percent's really a fraction. You know, sometimes this is confusing, but it shouldn't be that confusing. Like if you had, like what's 50% of $100? It's $50, right? It's not $5,000, you know? So like the percent is a fraction. We just write it times 100% to express the number in a whole number. So you can multiply this by 100% and it's the same math, or you can not multiply it by 100% if that confuses you. It makes you think you just taken the number up 2 orders of magnitude. So multiply by 100% or not, but then multiply that by 100 grams. So if you do 100 times 2 times 1.008 divide by 18.02, we get 11.19 grams. And don't multiply it by 100, multiply by 100%, which is not multiplying it by anything, right? Does that? So again, sometimes percentages are confusing. Just remember, we don't need to really multiply this number by 100 and turn it into 1,100 grams. That's 11.19 grams of our 100-gram sample is the hydrogen. The remaining mass is oxygen. Okay, so I always like to think for a lot of problems, there's going to be more than one way to go through dimensional analysis steps. Like I might show it one way, you might be thinking, could you do it this slightly different way? As long as your conversions are correct, as long as you're taking a proper conversion in the numerator versus denominator, and it just has to be an equality. Whatever's in the denominator has to equal whatever's in the numerator. When I'm saying 1 mole of hydrogen is 6.022 times 10 to the 23 atoms of hydrogen, that's a simple equality that works. So we just have to think, as long as it's an equality, as long as it's true, if I can do a dimensional analysis step in a different order, in a different way, and get the same number, then you just found a alternate way or a second way or a third way to find a number. Okay, let me throw a question. You guys haven't done this in a while where I just give you a problem. Just you have 4.72 grams of magnesium nitrate. Try to work out how many grams, how many atoms of nitrogen are in that sample. I'll give you guys about 2 or 3 minutes. This might take you a minute or two. As always, you can compare with your neighbors and chat if you want. All right, we'll take a look. I still see some of you guys working, but if you're on the right track here, I think your first thought's going to be one of two things. I either need to think, I think grams to mole is probably the only starting point here. Is like the first part. Is just, we got to somehow get to mole here. And I suppose we can convert grams to AMU. If you convert a number of grams to a number of AMU, that's a fair starting point too, I suppose. But probably the most obvious starting point would be to calculate the formula weight here, but as a molar mass. So the molar mass would be 148.3 grams per mole. Of course, that's or AMU, same number. But I'm probably thinking the molar mass here, so I can go for every 148.3 grams of magnesium nitrate, so the mass cancels, that's 1 mole of magnesium nitrate. And then now I do have a couple of choices. Do I want to go moles into units of this compound? Or do I want to go into moles of this versus moles of nitrogen in the sample? We could do it that way too. I could say for every mole of magnesium nitrate, there has to be 2 moles of N, because there's twice as much N in the sample as there is magnesium nitrate in terms of like the unit. So every 1 unit of MgNO32, that's 2 units of N. So I have a few options here on how I can approach this problem. I think I'm going to do this one where I think for every 1 mole of magnesium nitrate that I have an Avogadro's number of that unit. And I'm going to write that as units. Of MgNO32, just to get us thinking of this. That the unit of MgNO32 would be molecules if it were a molecule. It would be just like in that specific formula. So the units of MgNO32 means a unit of MgNO32 is literally 1 magnesium and then 2 nitrate ions. And so it's really the thought of like if this were a molecular compound, this would be an Avogadro's number of that molecule, which is not a molecule. So we just introduced the word unit. Maybe makes it a little bit more confusing, but it hopefully isn't confusing. It's just literally 1 magnesium ion, 2 nitrate ions is that unit. And then so for every 1 unit of magnesium nitrate, we have 2 nitrogen atoms. So we're just looking here, we have 2 nitrogens. And then that should be it. So we've gone from grams to moles of magnesium nitrate, from moles of magnesium nitrate to units of the formula, and that units of the formula to the nitrogen atom. So if I go 4.72 divided by 148.3 times Avogadro's number, and then times 2, should get me to the right answer. And so that ends up being answer C. Of 3.83 times 10 to the 22. Okay, so that's kind of how we approach a problem, just like on like an exam type problem on how to calculate the number of, say, nitrogen atoms in a sample of magnesium nitrate. Okay, so the kind of like the closing out the middle section, section 3.5 of chapter 3 that we're kind of building toward is then getting formulas from chemical analysis. And so the analysis we can generally do is get the percent mass of the elements within a compound. And so we can get the percent mass of a pure substance that can help us get the empirical formula. And so this whole part here, the percent by mass of a pure substance or compound can get us the empirical formula. That's the whole idea, that if we knew the percent carbon versus hydrogen and C2H2 or C6H6, because empirical formulas all share the same percent by mass, then the best we can do with percent by mass data is the empirical formula. Hopefully you understand that we can't directly get the molecular formula from this one analysis. The best we can do is the empirical formula. We mentioned before, for molecules, the empirical formula is kind of not what we really want to know. We really want to know the molecular formula. We really want to know the molecular weight. And so to get the molecular formula, we have to devise a way to determine the molecular weight. Well, one of those ways is that mass spectrometry experiment, which I can say we probably don't really understand how it works. I can also say to you, if you really want to understand how a mass spectrometer works, that's like upper level chemistry. That's like senior level chemistry stuff. But if you appreciate that technique of studying things in that type of device can give you molecular weight data. It can give you atomic weight abundance data, and it can give you a molecular weight very precisely. And so you can get precise molecular weight data from that type of an experiment. So I think that the take-home message is that experimentally, we can do experiments. You put a chemical into a device, it'll tell you the percent by mass data. That's like one type of instrument that's available to us in the lab. Another device is something like a mass spectrometer that can very easily give us something like a molecular weight. And so just a couple common experiments can be done to get a molecular weight. And if you knew the empirical formula, let's just do CH real quick as an example. You know CH has an empirical formula weight of 12.01 plus 1.008, so that's about 13.02 AMU. If you knew a compound had a molecular weight of 26 versus 78, you can identify if it was C2H2 versus C6H6. So the whole idea would be, if you knew the molecular weight, let's say the molecular weight was 52.06, let's say. So if we knew the molecular weight for this molecule that had this empirical formula, CH was 52.06 AMU, divide 13.2 into that. What do we get? 52.06 divided by 13 is 4. So if we take the molecular weight, divide by the empirical formula weight, then we determine the number of multiples of that empirical formula in the molecular formula. So if you know the empirical formula, if we determine that from data, we can then take a molecular weight and see how many units of that empirical formula there are in one molecule. So that could be how we could determine something had a formula of C4H4. Okay, just to understand the whole process, get an empirical formula, get a molecular weight to see how many multiples of that empirical unit there are in one unit of the molecule. Okay, and we'll see some examples of that, throwing that together within the actual context of examples that kind of look like this one here. So let's say we have a compound that's now 84.4% carbon, 15.4% hydrogen, those are by masses. It has a molecular weight of 142 AMU. What's the molecular formula? Now, you can devise a way to do this in a couple of different steps that don't go through this process here, but the whole point of this process is really for us to understand that this data here gets us the empirical formula. So treat this like a two-step problem. Step one is to find the empirical formula. And then step two is to find the molecular weight, or find the molecular formula using the molecular weight. And so with the way we give you the information in this problem, you might be very clever and you can come up with a way to get the molecular formula maybe in one step. But we're really thinking of this problem like a two-step problem. One experiment's getting us data to get the empirical formula. Let's see how to do that part of the problem. And then the second step of the problem would be, well, let's take that empirical formula we get and think of how many units there are using the molecular weight. And so, so for step one here, finding the empirical formula, what I need to do is I need to start with like mass ratios. We have percent by mass. I need to start with two mass ratios that are just true for those percentages. There's a lot of problems like this. The problem in high school to me, and even in our book I think says this too, is to assume a 100-gram sample. I don't really give a crap what sample you assume. I want us to assume a set of masses that is correct for that data. You know, I just want us to start with two masses that the ratio of the masses is 84.4 to 15.6% by mass carbon to hydrogen. The easiest way to do that is just to treat the percentages like masses, but we just have to start with ratios of mass that are indicative of those percentages, which is just easiest if you make those percentages grams. So the assumption here is really just assume you have a set of mass ratios that is 84.4% to 15.6%. Very easy if you just treat those masses as grams. And so then if you want the ratio of the molecules or the atoms or the moles of carbon versus hydrogen, we just have to go grams to moles and then start thinking of whole number ratios. So for carbon it's 12.01 grams per mole of carbon. And then for hydrogen it's 1.008 grams per mole of hydrogen. I'm just using whatever this is, 1 mole of hydrogen for the grams of hydrogen. So sometimes we get confused and they say, well, do I want to use H2 like for molecular hydrogen? No, this is mass of the H atom. We use the H atom molar mass. We use the C atom molar mass. And so if I stop and calculate these quantities here, 84.4 divided by 12.01 is 7.027. Now that's present in ratio in this sample to the carbon number of moles, 15.6 grams divided by 1.008 grams, that's 15.48 moles of hydrogen. Now that's just a specific mole ratio within the sample that we've started with. What I want to know for the formula is what's the simplest whole number ratio? Now, if I just said mathematically, find me that carbon to hydrogen whole number ratio from this data, again, you might have a few different ways you might think mathematically to do this. The way I think to do it, which isn't maybe there's a better mathematical way, I don't know. If there is, share it with me. But the only way I can think to do this easily is to divide both of them by the smallest number. Now, if I divide one by this number, I have to divide the other by the same number because these are ratios. This is the ratio of carbon to hydrogen. If I'm dividing one by a number, I have to divide the other by the same number because I'm just changing the ratio and hopefully at least getting one of them to be a whole number. So obviously this works out to be 1 mole of carbon present in ratio to what's not quite a whole number. I get 2.202 moles of hydrogen. Now you might think, can this be CH2? Probably not close enough to round. You should be really close to a whole number to round here. What I then start thinking is, well, what's my next multiple that I can multiply these by. So I start thinking, can I multiply these by a 2 and get a whole number? It's 4.4 for hydrogen, doesn't work. Do I need to multiply by 3? Well, that's 6.6, that doesn't work. Do I need to multiply by 4? Because we're trying to get the whole number ratios. My carbon's already a 1. I can't multiply by a fraction anymore. It's got to be a whole number. So I'm just like going up in whole numbers, and I stop at 5 because then I get 2.2 times 5 is 11. And then times 5 onto the 1 of carbon is C5. So I get C5H11 for that formula. And then the next thought's going to be, well, what's the empirical formula weight of that? Turns out it's about 71. We'll show this next time to make sure we see this. That's about 71 AMU. The molecular weight's 142. So what do you think the molecular formula is? There's going to be 2 units here. It's C10H22. It's just decane. But we'll wrap up and we'll go through this example again just to kind of highlight how you go from step 1 to step 2. So I went through really fast at the end. I'll rehammer that out to start a class on Friday. All right, guys, that'll do it for today. Have a great day, and I'll see you next time.